So the porometers, which we will use in the next video, so like this one, you know they measure stomatal conductance or resistance. But if you want to link those measurements to the ones of the scale, you will need something like this. I think that most of you have seen this kind of schemes, maybe in high school or otherwise in your undergrad, in classes about physics or electricity. Normally you have an electrical circuit, and then you know that here you have resistances that are in parallel, and well, the current, the electric current passes different resistances, and then they come together. And I also assume that you can do excuse me, you can make calculations on that, right? Now this electricity here, this principle of electricity, you can also apply it to water movement in a plant or in a leaf. And this over here represents a leaf. So here you have water, which actually just well, evaporated from the cells of the plant, let's say. So we're in the intercellular space here. And what the water can do now is escape to the outside environment on the right. But a water molecule has options. It can either escape from the upper side of the leaf or from the lower side of a leaf, from this side. And then it passes some once there. So imagine we take the upper side, the adaxial side, and lower side is abaxial. People who speak Dutch, for people who speak Dutch, there is an easy trick, which means that the Dutch word for roof is dak, and you know that's usually on top. So that's an easy trick to use. In English, I don't know. Anyways, but then the water passes here, and then there is the stomata. And stomata, of course, a plant can regulate how much they're opened, and that's what this arrow represents. But this is exactly, so this stomatal conductance in the environmental conditions here in this room at this moment, because a plant can change that, but in these conditions, so that's exactly what we will measure. Well, on the upper side of the leaf and also the lower side of the leaf. Actually, it does not only depend, this stomatal resistance or conductance, does not only depend on the stomatal opening of individual stomata, but of course also how many a leaf has. So it's also a function of that. And it could differ between the upper and lower side. And that depends also on plant species, also on the position of the leaf on the plant, on the plant or the size and so on. So that's the first thing. And then once the molecule has passed the stomata, there is this boundary layer resistance, which I already explained just in the previous video, which depends on the wind speed. Now in this case, there is no wind here. So depending on which data you use, I think, from which group, you will either have a measured value or a calculated value. And then we go out. And you know, of course, I guess that these two resistances, when you work with resistances, watch out because conductances are 1 divided by the resistance. If you work with resistances, this one plus this one is the total resistance for the upper side. And analogous for the lower side. And then if we replace this as if it's one resistance and this one as if it's one, then the total resistance here, well, there's a formula for that, and what that is 1 divided by this total resistance is equal to 1 divided by this total resistance plus 1 divided by this total resistance. That's how to do it. And then in the practical notes, you will see a formula which allows you to calculate the transpiration at the leaf level. And what you need to do is really calculate that for every leaf individually. That's what I would do to avoid mistakes. And what you should do there is multiply, if I'm not mistaken, the conductance. So that's 1 divided by the total resistance. Multiply that conductance by a water concentration gradient. And a water concentration gradient is the difference in the water vapor concentration in the leaf and the outside environment. And for that, you also need the measurements which we just did with this red device over here. What you will need for that is the temperature over here and the humidity. In a plant leaf, you can assume that humidity is 100% of the water. When it just evaporates, you know, a plant, it contains a lot of water. So humidity there is 100%. And you can assume for this practical that the leaf temperature is the same than the temperature of the outside environment. That's also important. Yeah. And so imagine is 20 degrees here. And, well, in the leaf, the humidity is 100%, and outside here is 68%. Well, they need to convert these percentages and temperatures to actual water vapor concentrations. And the larger the water vapor concentration gradient, so the difference in these concentrations between leaf and air, the faster the water will move out, and so the higher the transpiration will be. All right. Well, I guess that's about it for this section.